the future trends in this particular domain, research domain. So, as a mechanical engineer, what is the role of engineering in biological environment, where we are connected with biological system? What is our role? What we are going to do with biomedical engineering field? Truly, we require mechanical engineers in solving biomedical engineering problems or not? Hope I'm audible.
Yes, sir, you are audible.
Thank you. Thank you. Thank you. So the success of any material to be used as a biomaterial in medical devices, apart from biocompatibility, is often related to the ability and ease of the material that is to be formed into complicated shapes. We'll discuss in a detailed way what is a biocompatibility, how to test it, and a little bit later. I think a few sessions might have discussed about this unique nature. Like we cannot use any material inside our body because our system, the biological system, has to accept the material which is being used as a device or implants or scaffolds, etc. The biological system is a complicated one. We don't have any direct software to model bones, tissues, etc. The reason because every shape or every biological system has its own nature. Like my own bone system cannot suit for others. There is a generic model that is available in order to exchange or in order to use as a replacement for my skin or my bone, etc. So this is the pictures I used from references like a normal knee compared with the arthrosis of the knee. Now the biological system has a combination of hard as well as soft tissues. There are various materials used here, or biological nature has developed its own system of materials. Like the tibia is connected with other bone by means of a cartilage, which is soft in nature. Cartilage is a soft material which is used as a cushioning material for certain purposes. Now, when the tissue material or the cartilage is damaged due to continuous use or any accidents, the bone will get direct contact that will produce large amount of pain to the patients. Now, in order to avoid or in order to do repair work, as a mechanical engineer, I can speak like repairing of human parts. I need to perform two operations or two tasks. Like I have to design for the existing one or existing part, and I need to identify a suitable material. Also, I need to find out a suitable fabrication technique. Now, in the evolution stage of materials, I will be performing many number of tests whether my material will sustain all the requirements demanded by the nature, like a tensile strength or compression strength or it may be compatibility with the biological environment, or it permits the bone to grow, or it permits blood to flow. So many kind of requirements to be investigated before I introduce a new material. Similarly, I need to identify a suitable methodology to design a complicated shape, either by means of uh, scanning the parts through MRI or CT scan, etc., or even X-ray. Then, as it is a complex in nature, the next responsibility of mechanical engineer is to identify a suitable manufacturing process to manufacture it and how to fix it. Now, to study the biomaterials, focuses on issues such as biocompatibility, host tissue reaction to implants, cytotoxicity, and basic structure property relationships. So these are all the uh, uh, properties I need to investigate before evolve with any new materials. Now, the biocompatibility, host tissue reaction or reaction to implants, cytotoxicity, and basic structure property relationships provide a strong scientific basis for a clear understanding of many successful medical devices, such as mechanical heart valve. One such example I want to quote. You can see that uh, this is a heart valve working nicely till our life ends. Am I right? Somebody can answer that. What is the total cycle it has to go through for an average life of 70 years, for an example? Anybody can tell me? This much number of cycles it has to cover, or it has to work successfully or comfortably. So the average heartbeat of a human is around 70 to 100. Am I right? In the range of 70 to 100 beats per minute.
Yes, sir.
Yeah. Okay. You multiply that with 24 hours into 60 minutes into 365 days multiplied by 70 years. Now it comes around trillions. Am I right? What is the fatigue life of stainless steel? Any idea? What is the fatigue life of a rubber? Now we cannot compete with nature. The reason because no material is so far evolved to replace such a very long life. Am I right? There is no material evolved so far. See, if a material is designed for covering a total life of 10 power 6, that is million cycles, it is a great success of human. Some material may extend its life to 10 power 7 or 10 power 8 cycles, number of cycles. But here we have more than that. We have more than that. See, it has to work for large number of time. It has to cover large number of cycles. So in general, it is a one-way valve that allows blood to flow in one direction through the chambers of the heart. A mammalian heart usually has four valves. The valves determine the direction of blood flow through the heart, and heart valves are opened and closed by blood pressure. Blood pressure. So, say this is a simple simulation which shows the working principle of a heart valve, mechanical heart valve, so that it permits the blood to flow in only one direction. It's a one-directional valve, so the blood will not come back, so it will flow from a location to other in a one direction, following a one direction. Now, these are all few examples of already evolved system and their life period. Like anti-vibration spring has 2.1 million cycles, damping spring for rail vehicle 3.5 million cycle, heart valve. I think it has wrongly calculated 7.056 million cycles. It is more than that, nearly 200 million cycles. 200 million cycles. I have to correct it. Somebody can calculate and tell me what is the million cycles the heart valve has to cover. So when I see the natural rubber embedded with carbon black, the different percentage of reinforcements like 10, 20, 35 has cycle failure around 1.5 million, 1.5 million. And natural rubber with the CNT has slightly increased from 1 lakh to 1.75 lakhs, 1.75 lakhs times. So these are all few examples of heart valves, which was designed for many applications. Electrospun heart valve, a custom 3D printed heart valve, 3D model collagen fiber architecture, natively flat fibers to mimic. Then let us see what is the biomaterials, or first we'll see what is biomaterials, and then we'll get into biocomposites exactly. So biomaterials must have special properties that can be tailored to meet the needs of a particular application as it is demanded. Like the material which is designed for a particular application needs to satisfy certain conditions like the behavior of the material in the atmospheric temperature is different when it is kept inside our body. The temperature is different. It is involved in fluid interaction. There are many chemical reactions will be taking place inside, because of which there are secondary effects. There are so many things happening when you design a material. So a biomaterial must be compatible in biological environment, a non-carcinogenic, corrosion resistance, and has a low toxicity as well as wear. Now, the engineer's role is to engineer specifically to cooperate with the biological system for a multitude of purposes that are often called biomaterials. As usual, all the three different type of materials can be used as a biological material, like metals, metal alloys, polymers, ceramics, bioglasses, and everything between. Generally, it is classified as metal, ceramics, and polymers, and we have its own additional or subcategory also, like metals adding with alloys, polymers adding with alloys, ceramics and their alloys, not alloys but reinforcements. Okay. So the biomaterials field of material science continues to grow rapidly as it touches on life-changing medical applications, including implant materials, materials for therapeutics, and then materials for tissue scaffolds, materials for sensing devices, as well as diagnostic probes. So a biocomposite, as we discussed earlier, like should have a particular, it has to satisfy a particular environment. The reason because biological environment are different in nature. Now, the material which is designed should have all these categories like or characteristics like bio-inert. It should be inert with the biological environment. Means that it does not react or initiate a host reaction when in contact with the biological tissue or systems, or it is a ability to make direct or close contact with the host tissue. That is, we have to ensure that there is no harmful effect happened or host reaction happened when it is in contact with the biological tissue. Now, the picture illustrates all these four important characteristics like bio tolerant, bio inert, bioactive, biodegradable. All these characteristics are expected highly while designing biomaterials. Bioactive in the sense it has to initiate a host response or a material tissue interfacial reaction. The bioactive materials often instigate chemical bonds between host tissue and themselves through different biophysical as well as biochemical reactions. Somebody can tell me an example of bioactive where it is expected that chemical bonds and the host tissues are to be involved in the system. I need interaction from the participants uh, for the meaningful discussion. Can you hear me? Hello.
Yes, sir, you are audible, sir.
Okay. Okay. Yeah. Oh, thank you. See, suppose I use a screw um, to fix my tooth on the jaw bones, right? If it is a bioactive, the material what I have chosen for connecting or for fixing my tooth with the jaw bones, it will emphasize that fixation is very good if it is bioactive. Similarly, biotolerant, the materials that are separated from the host tissue by a fibrous capsule generated by corrosion products or chemicals released between the implanted materials and host tissue are normally termed as biotolerant. So these materials are not rejected by the host tissue, but they are separated from direct contact by this fibrous tissue layer. Another important characteristics or the property expected from the biomaterial is biodegradability. Here, the materials are able to dissolve on various time scales in bodily fluids as well as tissues. So these materials have applications in controlled direct release, sutures, and wound healing. So confusingly, each of these terms is sometimes used interchangeably with the word biocompatible, broadly meaning the material is not harmful to the host tissue. This is on a nutshell, I want to conclude that biocompatible is nothing but the material is not harmful to the host tissue. That is important information I want to convey. Now, biodegradable property helps the um patient to recommend not to go for a secondary operation. We know that in olden days, if a bone is connected by means of keeping plates inside made of stainless steel or titanium, after a period of time, it will be removed. The implants or the plates will be removed uh, by performing the secondary operation. Now it is not required. The reason because there are materials identified which is biodegradable in nature. Also, it permits the bone to grow in a very faster way, or it helps in bone healing quickly. So the secondary operation is not a case now. It will be degraded and um come out as in the form of fluids or in the form of solids, etc. See, however, depending on the application, differing requirements may arise. So, in the case of tissue engineering of the bone, for instance, the polymeric scaffold needs to be biodegradable so that as the cell generate their own extracellular matrices, the polymeric biomaterials will be completely replaced over time with the patient's own tissue. In the case of mechanical heart valves, on the other hand, materials to be biostable, wear resistant, and which do not degrade with time. When a heart valve is replaced by means of mechanical heart valves, I don't expect that very similar to the polymeric scaffold, which was used for bone fixation. It should not degrade. It should not degrade with time because it has to retain for a long time. The material has to be present inside our body in order to make the system very successful. So materials such as pyrolytic carbon leaflet and titanium housing are used because they can last at least 20 years or more. So people will live with the materials, third particle or third foreign material inside for their own life periods. So when you see the classification of biomaterials, it is given as biological materials or synthetic biomedical materials. Examples are soft tissue, normally found in the locations where skin, tendon, pericardium, cornea, for which a synthetic biomaterial, equivalent synthetic biomaterial, medical materials are polymeric in nature, namely ultra high molecular weight polyethylene, PMMA, PEEK, PU, silicon, PTFE, etc. Then, in order to replace the hard tissues, metallic materials are suggested, like stainless steel, cobalt-based alloy, titanium alloy, gold, platinum, etc. So, hard tissues in the sense it is a bone structure or dentin or a cuticle, etc. Or the hard tissue may be replaced by means of ceramics like alumina, zirconia, carbon, hydroxyapatite, tricalcium phosphate, bioglass, calcium aluminate, etc. Or it may be a replacement with composite, like carbon fiber reinforced with a PEEK material, or carbon fiber reinforced with UHM WPE, or carbon fiber reinforced with PMMA, zirconia, silica, BIS, GMA, etc. So these are all the variety of biomaterials normally found in a biological environment. Those materials are already proven that it is very good in biocompatibility, properties like biocompatibility, bioinert, etc., etc. Now, as a general introduction, I just would like to say that composites are the materials that contain two or more distinct constituent phases on a scale larger than that of atomic. Compared to the traditional homogeneous materials such as metals, ceramics, and polymers, the main advantage of composite is that they are mechanical, biological, and other physical properties that can be tailored to the requirements of specific applications. Suppose I need a weight is a property to be reduced, but the strength has to be increased. Uh, that is the requirement demanded by the structure has demanded for high strength, low weight, porous density, porosity. So I can tailor whatever the property expected by the design or demanded by the design. So though a composite can be made of two or more constituents, in most cases, the composite comprises only two constituents. One is the matrix phase, and the other one is the reinforcing phase. We know that the matrix phase is continuous and provides the overall form. The shape of the material is completely derived by means of, or the role of matrix is to derive the shape because it is continuous in nature. A reinforcing phase, such as fibers or particulates, is generally stronger than the matrix. That is the uh, idea behind fabricating any composites. So it should have two phases. One is acting like a matrix, which is soft in nature, and the other one is hard in nature, but it should be the amount of inclusion may be controllable. Now, composites may be formed or fabricated by integrating two different phases of materials in different forms. Like composites may be reinforced by particles, or the reinforcement is in the form of particles, or a chopped strands, or unidirectional composites, laminates, or fabric reinforced plastics, honeycomb composite structure, etc. Now, based on the applications, I have summarized like what are the different matrix and reinforcement are generally used, and what is the expected properties of those composites. In the case of automobile tires, a rubber is taken as a matrix, and carbon black particles are used as reinforcement with the expected properties of enhanced tensile strength, enhanced toughness, and enhanced abrasion resistance. So these are the properties expected from this particular composite. Or in the manufacturing side, cobalt or nickel, reinforcement is tungsten carbide or titanium carbide with the expected properties of high wear applications like cutting tools for hardened steels. Now, the cutting tools are made from composites, integrating two different phases of material. One is a cobalt or nickel, the ductile kind of material, and the other one is ceramic-like structure, the tungsten carbide or titanium carbide, etc. Or the case of wear applications, a matrix is used, aluminum is used as a matrix, and silicon carbide or aluminum oxide or the reinforcement with the expected property of wear resistance. And electronics, now we are talking about conductive polymers, where electrical conductivities are enabled to connect from one place to other, even though it is made of polymer materials. Now, the reinforcement or the agent which conducts the electrical property of the material by what do you call this? Developing a roadmap or a route map like tungsten or ceramic particles, especially expected properties are dielectric or permittivity. Then the mechanical properties that are expected from the biomaterials are it should have a large amount of modulus of elasticity, which describes the stiffness of the material, and it is usually obtained from the slope of the stress and diagram. We know that what is the modulus of elasticity. Then ultimate tensile strength is another mechanical properties expected from biomaterials, elongation to failure, fracture toughness, etc. So among which the fracture toughness is an important measurement of the material's resistance to crack propagation. So when you see the modulus of velocity of different materials used in a biomedical applications, so starting from soft tissues, polymers, tricalcium phosphate, bone, hydrox apatite, etc., we have a different type of X modulus every material we process. Say alumina has a maximum of 414, cobalt chromium 234 MPa, GPa, and then stainless steel is 193, hydroxyapatite is 62, bone 21, tricalcium phosphate, it is around 7, polymers 3 GPa, soft tissues, that is X modulus is less than that of 0, less than that of 0. Also, the ultimate strength of different materials, what we have discussed in this uh, picture, has its own values, like polymers takes a value of 69 MPa, and then bone is 138, alumina it is 448, so titanium it is 1172, 1172, for an example. Now there are reasons behind why these two properties are compared in the case of biomaterials. So when you see the modulus of elasticity of the bone, which is around 21 G, when I use stainless steel as the material for making implant to connect a broken bone, obviously entire load will be taken care by the implant, not the bone, right? It do not or the difference of the X modulus makes the bone to stress high. I think we'll come a little bit later. What is a stress shielding and all. So nowadays, understood that material which is or whose X modulus or the ultimate tensile strength is closer to a bone material needs to be evolved. So there are many researchers attempted fabricating or doing research on different materials to bring down the stress shielding effect of bones, and they have succeeded with a few attempts. Let us have some idea about what is stress shielding and a little bit later. So biocomposites are a special form of composites which can be used in biomedical applications, either inside or in contact with the human body. It may be used as an implant so that it will be kept inside our body, or it is made as a device so that it will have a physical contact with the human. So the key advantage of composites over monolithic materials is that the material properties of composites can be tailored according to different requirements in the mechanical, chemical, biological, and other physical aspects. So this is achieved by altering the composition, interfacial bonding, physical arrangement of the constituent phases in the composites. So these are all few examples of various devices and implants used inside or outside the body. The first one, on the left side, you have a polymer material used for making implants, sutures, or connectors, or plates for connecting broken bones or tissue repair, or it may be used for dental implants, etc. Now, these devices are kept inside the body, so it has a direct contact with the physical environment. The biological environment. Right. Now, it should have the properties expected by the biological requirements, like biocompatibility, suitable strength, and then degradation nature, etc. And there are certain devices used for detecting certain parameters of the biological environment, but it is by means of a physical contact, not kept inside the body. Say, for example, identifying the level of glucose, hydrogen peroxide, uric acid, presence of uric acid, ascorbic acid, dopamine, cholesterol, amino acids, cancer cells, etc. Now, all these parameters are measured by means of electrochemical electrochemical methods. And one such example I want to show you, I want to tell you like glucose meter. So I think now every house you have a blood pressure sensor as well as glucometer. Now the glucometer has a short interaction with the human body, which is capable of detecting the level of glucose present in the blood, right? So it has a short contact with the physical body. There are screws, bioscrews used for implanting the uh, dental applications. You have on the right side you have a healthy dental structure and the implant structures. Both it is given. Uh, Now the tooth are fixed on the jawbone by means of a screw which is drilled inside, and then you'll put a cap over it. Now this screw takes responsibility of holding the tooth with the bone. Is it fine? Any clarification now? You please stop me whenever you require, so that we'll discuss and go along with the presentation. Shall I proceed?
Yes, sir. Please proceed.
Okay. Now, this is an example of physical contact sensors used for biomedical applications. It may be in the form of uh, sensors. So there are switch sensors, which is capable of predicting the ions, presence of ions, glucose, lactate, and there are ISF sensors used for sensing the glucose level, alcohol content, cortisol, and there are watches, smart watches, able to detect many informations like even your heartbeat can be detected by means of electronic smart watches. Am I right? Those are all called wearable electronics. Wearable electronics. Now it is a trend of the researchers to work in this flexible electronic, polymer flexible electronics. There are rings used to identify the ECG, heart rate, temperature, blood pressure, body positions, etc. Uh, and this can be sensed to, or the data sensed by this particular ring can be sent to a doctor through Wi-Fi or any communication way. So when you see the different kind of composites, um, uh, there are categorized as a polymer synthetic polymer, natural polymer, nanomaterial based composites, hybrids. The examples of different materials used in the biomedical applications, like polymer synthetic materials, example as PLA or PCL, PLGA or PEG, natural polymer composites like collagen, gelatin, chitosan, alginate, silk fibroin, and then nanomaterial based composites that the polymer reinforced with the graphene oxide or graphene, carbon nanotubes, hydroxyapatite, silica nanoparticles, etc. Or it may be a combination of hydrogen and fiber, like porous foams, retrospun fiber mats, 3D printed lattice scaffolds, core shell and multi-layer constructs, ceramic reinforcement like hydroxyapatite, tricalcium phosphate, bioactive glasses, calcium phosphate cements, etc. Now, to show you what is a lattice scaffolds, I have printed a few structures. Just I'll connect my camera so that you'll see that. Are you able to see my camera?
Yes, yes, sir.
Yes, sir. Yes, yes.
This is one such structure we printed using our 3D printer, polymer 3D printer, FDM technique. And like a ball, right? You see how the structure is. We save large amount of material. At the same time, it permits it won't affect any flow of blood, right? It has its own, in one direction it is holes, other direction there is no hole. It will permit only one directional flow. See here. This is another lattice structure printed with the help of FDM. It is a PLA material is PLA. It is very strong in compression. It is very strong. I think if possible, I'll show you the stress and diagram of this particular material or the structure tomorrow, because we have conducted already a compression test of this particular block. These are all designed for scaffolds, and we use SolidWorks to design this. This is another structure. I'll tell you the application where it is being applied. Say, for example, I have an implant used to connect the hip with the leg, right? This is the ball. It's a solid phase. And from here to here, the structure what we have followed is the same. The same structure. Lattice structure has been used for two different purposes. One is enhancing the contact so that a strong binding between bone as well as the implant and the bone. And other one is it will help the tissue to grow in a faster way, right? There's another bone printed for showing like femur bone. This is a cartilage. So that it will be assembled here. It is printed from SLA printer. Plastic material is plastic resin as the material, right? And this is another lattice structure. I'll show you the exact model. It is only a surface, right? But it is very strong in nature. This model is downloaded from GrabCAD but the design, the structural element is taken from GrabCAD, but the design we develop in our software, SolidWorks software, correct? So now the idea is any intricate shape can be printed now with the help of 3D printing technique. So apart from the material property, the structure also play a major role in developing the new materials for biomedical applications. Different kind of composites that are used as a biomaterials are very similar to the general composite. We have continuous fiber composites, particulate composites, short fiber composites. Now, the fibers used here are for developing screws, total hip stems. What I have shown here is a stem. By adopting various fabrication technique like injection molding or a 3D printer or extrusion, etc. In the case of particulate composites, we have powders are used as a reinforcement, especially for dental resins, bone cements, bone grafts are the examples of particulate composites. In the case of continuous fiber composites, we have two different categories like 2D composites and 3D composites. It may be a unidirectional laminates or it may be a tape laminates, so that bone plates are constructed with the help of UD laminates. Total hip stems can be fabricated by means of tape laminate. Then, in the case of 3D composites, we have unidirectional rods, knitted composites, braided composites, woven composites, stitched composites, non-woven composites, especially for used in dental post, sockets, bone plates, spine rods, etc. So this is the two-dimensional UD fabricates or UD laminates. Here, tape laminates used for doing repair works of any bones. There are continuous fibers used as reinforcement for making three-dimensional composites. A carbon fiber or nanotubes are used as unidirectional rods, or it may be a knitted structure like this, or it is a braided, or we have a woven, etc. Now the question is, why biocomposites for tissue engineering? The reasons are, it will mimic the native extracellular matrix, ECM, and it is a tailorable mechanical and degradation properties and promote cell adhesion, proliferation, and differentiation. And the key design requirements are biocompatibility, biodegradability at a controlled rate of controlled environment rate, mechanical match to target issue, and then porosity and interconnectivity, processability, and sterility. Now, till today, the majority of the biomedical devices used either as implants in the human body or as external prostheses that are made of biocompatible homogeneous material such as metal, ceramics, or polymers. However, there are recognized limitations in these monolithic material devices. Examples are, the most implants in orthopedic surgery are made of metals. Their drawbacks include, it is too stiff to handle, such that a stress protection of the fractured bone can occur during healing. Considerable artifacts are produced under X-ray, which make the interpretation of radiographs difficult. Metal sensitization can occur, and the implants may cause mutagenicity, that is the ability of substance to cause permanent heritable changes to an organism's genetic materials. Even the DNA can be changed because of the reaction happened with metal as well as the biological environment. In contrast, these drawbacks can be overcome if implants are made of polymer matrix composites. That is why most of the work now, or most of the researchers are diverting their area from metal and ceramics to polymer matrix composites. See, moreover, biodegradable implants can be developed based on composite technology, which no longer needs a second operation to remove the implants once are fixed into host tissues. This unique feature is not present in any metal implant. If it is a if implant is made from a metal, definitely he has to go for a secondary operation or surgery. So a biomedical device can be an external prosthesis or an implant used within the human body. So an implant then needs to be in contact with the host tissues. The human tissues can be categorized as hard and soft tissues. Only bones, teeth, and cartilages are hard tissues. All other tissues are the soft category. So in this respect, the biomedical applications of composites can be grouped into those for hard tissues as well as soft tissues. And then biodegradable compounds are those that have ability to decompose into biomass, methane, water, carbon dioxide, as well as inorganic compounds. And then this group of polymers are non-toxic and can undergo biological enzymes and various non-enzymatic process, including chemical hydrolysis. Okay, let us see the applications of biomaterials in the human. You can just get to know that how many locations the biomaterials are employed in the human body. It is used for dental post, dental arc wire, and dental restorative material, or it may be used for bone replacement, vascular graft, abdominal wall prosthesis, intramedullary nails to connect bones, cracked bones, or broken bones. That may be used in a tendon and ligament replacement, or cartilage replacement, or to connect bones by means of plate and screws, or it may be a total knee replacement so that the socket, ball and socket may be replaced by means of a new material, external fixation, or it may be a total hip replacement. Bone cement could be used for implanting the material with the bones, spine cage, plate, rods, screws, expanding jaws, finger joints, etc., etc. There are so many applications where so many applications found in
rapid prototyping technologies to produce implants, but not to the scale of what BHU has done. So if you go to BHU, they have a complete technology package for the biomedical application. They have a very good, very old metallurgical engineering department. So I suggest the people can refer to the articles which is published by the BHU professors and the BHU doctors. So it is a collaborative publication. They do collaborative work. So anyone cannot biomedical doctors or the end users. Their input also is very much in necessity to produce the biomedical engineering application. So biomedical engineering applications, which is one of the latest field of engineering, it basically applies your engineering principles to healthcare products or life science products. So it basically tries to develop medical devices, healthcare devices, and diagnostic tools and therapeutic system. So in biomedical engineering, if you see, even your image processing will come into a biomedical engineering. But for our case, we are restricting us only to the additive manufacturing part, the biomedical implants, the biomedical uh, components which are placed inside the human body. Even your image processing, the MRI scanning technology, the X-ray technology, everything comes under the biomedical engineering application. But we are not going to. That is not a part of the our discussion. So if you see the biomaterial, you have different materials used so far. In earlier days, people used metal and alloys. Primarily, stainless steel were used, and later people started to use titanium alloys. So titanium 6-4 alloy is primarily used. And in the earlier days, people were using only stainless steel alloys before the advent of the technology of processing and using titanium. Stainless steel was used. And one of the very drawback of stainless steel is it has the content of chromium. Chromium is present in stainless steel, and this chromium is actually a heavy metal, and this was leading to some uh, occurrence of uh, cancer inside the patients where the implants are uh, implanted inside those patients. So maybe around some 30 years, 40 years back, they had this stainless steel implant. Later, after we had the titanium technology, people moved to the titanium technology, and whereas the implants are made up of titanium metal, like plates, screws. Uh, if you go through the implants that are made up of titanium, it is from it is a very expensive list. And once this technology, I mean, this was the technology earlier, but nowadays we have the polymer based biomaterials. The polymer, in the sense, it uses polylactic acid. This is one of the best, I mean, this is one of the widely used polymer, which has a very good biocompatibility. And we also have ABS. We have certain use, certain limited applications in the biomedical engineering field. And even the drug delivery, the drug which is delivered to us inside our body, will have the cytosine based biomaterial. Cytosine is something like it's a byproduct. It's a product that is derived from the prawns. I mean, you would have come across the seafood, right? You take prawn shell will have the cytosine material, and this cytosine material is used to deliver drugs into the human body. So that was the later development that took place. And nowadays we have the ceramic materials, like uh, the titanium oxides, glasses, even the specialized glass, which are used specifically in the dental implants. So these ceramic materials will be in the form of a toothpaste. The texture will be in the form of a toothpaste, which will be used to print the components. Nowadays we have the dental implants are very much printed to the requirement of the end user. Earlier days, maybe 20 years back, 30 years back, if you want to create a dental implant, the dental implant will have a standard dimension. Maybe after implanting in our body, to accustom to get the patient to get accustomed to the dental implant, it will take some time. But whereas nowadays they produce this dental implant very close to the end shape that is required. So this is one of the advantages. And composite materials like polyethylene, dental filling was also used in the case of dental implants. But whereas primarily in the case of FDM, where we use FDM uses polymers like polylactic acid, ABS, and these polymers are used for producing additive manufacturing products by using FDM. So this is primarily used for drug delivery systems, where I told you the cytosine. The cytosine material is actually printed, and the drugs are actually implanted to that cytosine material, and which is actually fed into the human body. This cytosine material is actually biodegradable. It just degrades in the human body and does not create any deposits in the human body. Again, bone implant. Bone is another very common implant that is produced by FDM process. So applications, as I told you, the patient-specific implants and prosthetics can be produced by additive manufacturing, because each and every patient will have a different requirement. because each and every patient is unique. So they will have different requirement for their need. So that is how this additive manufacturing is actually helping biomedical engineering. So where you can do the specific uh, production, where you develop parts that is required specifically to a particular purpose. Moving forward, so why biomedical sector needs additive manufacturing? Because it enables, as I told you, it enables patient-specific implants. How this data is obtained? It is obtained from very high effective medical imaging. That nowadays we have CT scan, MRI scan. So the basic size and dimension of the part wherever you want to fit the implant is actually it is captured from the CT scan or MRI scan. So that's why, as an engineer, we cannot do this alone. We need to take the help of the doctors. We need to have collaborate with the physicians. Only then this is feasible in the case of biomedical applications. So this is one of the, initially the medical imaging is done through CT scanning or MRI scanning. Then you go for complex geometries. Whatever the complex geometries that is required can be produced by biomedical, produced by additive manufacturing. What is complex geometry? The lattice structures are porous structures. That is the recent advancement in the biomedical products. Earlier, we used to have solid metals. Say for the case when there is a plate that it has to be implanted into the human body, it is actually a solid material, which actually increases the weight of the. It actually increases the weight. That's why people transform from stainless steel to titanium. Compared to stainless steel, titanium is lesser in weight. So when you implant in the human body, it actually gives lesser load onto the joints and the human musculoskeletal structure. So this was later. The evolution was from stainless steel, then to titanium. Then nowadays we have the lattice and porous structure. So this lattice structure is what again I indicated you in the nature inspired structure. So the nature will have different lattice structures. Say for example, the honeybee, the beehive, what you have, will have a structure which is actually given by the nature. Because no one is actually the hexagonal structure what you have in the honeybee. It's a one of the very efficient structures. So that is actually a nature inspired structure. So such type of lattice structure can be produced by additive manufacturing. When you go for your traditional manufacturing methods like machining process, producing such type of lattice structure with porosity inside, that was very difficult. So that is one of the advantages of this additive manufacturing. How biomedical sector is actually gaining from additive manufacturing. Because why we need porous structure is because sometimes then you need to have the provision of the tissues and the muscles, primarily the tissues growing inside the implant. So that is one of the advancement they have in the medical field now. Initially, the implants were only of solid nature. The tissues will not grow around the implants. Nowadays, you have the bones and tissues are actually growing into the additive manufactured structures. That is a porous structure. So to produce porous structures and lattice structures, you need additive manufacturing. The other advantage is, as I told you earlier, the prototype creation. The prototype can be created in a quick time, and it can be done for the trials. Trials can be done quickly, which actually reduces the time for the overall treatment or overall application. And cost efficiency, it is not completely cost effective, but still it can reduce the design cycle. It can reduce the number of prototypes it is producing, so that the cost comes down. And low cost prosthetics and implants are made nowadays because of this additive manufacturing technology. So even though it may feel slightly costlier when you go for any sort of biomedical product, the cost is going to be on the higher side, but still it is compared to the earlier days, it is actually cost effective. And biocompatibility, this is what another important thing. The polylactic acid, this is a very good biocompatible material. This actually actually integrates with the human tissues. So actually the human tissues can grow on this biocompatible material. So which means that this implant, whatever we are going to uh, fix on the human body, will become a part of the human body. And that is one of the major advantage of this uh, biomedical, this additive manufacturing. And the other thing is sometimes these implants are also, this polylactic acid is also biodegradable inside the human body. After some time, maybe after 3 years or 4 years, this degrades inside the human body, and the tissues has grown around the uh, implant, so that it mimics the original condition of the bones or tissues. Whereas when you compare with your metallic implants, it does not mimics the original thing, it just gives you the support. Whereas in the case of biodegradable and biocompatible material, this can mimic the uh, original tissue and the bones gifted by the nature. Then on demand manufacturing, there's another important thing. So uh, the time to produce these components has come down, and on demand manufacturing, in the sense, it can suit your specific application. Say for example, my teeth may vary from another person's teeth, so the shape, the the requirement, the profile, everything can be matched to a near net shaped manufacturing condition. So you can produce this even at the an accuracy of 99% or even above. So that is one of the advantage of on-demand manufacturing with the help of additive manufacturing. So in short, this is one of the a conceptual image where you do the MRI scanning. So MRI scanning is a very highly efficient scanning. It can scan any part of the human body. It can give you the even the dimensions. It can dimensions of the different part of the human body can be taken from the MRI scan. And this actually is then converted into a CAD model. Either we can model it, or the direct image can be used to develop the CAD model. And after the design iteration, this can be printed using a 3D printed implant. So you can see there is a nozzle and the filament is actually coming in, and this actually prints the required part. So this is one of the uh, generic way of producing FDM based 3D printed implants. And future deposition modeling, which is the matter of our interest, as I told you earlier, this actually consists of filament. This filament is your material of your interest. It can be lactic acid, which is used there. It can be ABS material, and so these are some of the materials converted to a filament. So initially these materials, it may be in a powder form or maybe in a solid form, they will be extruded, and these filaments will be injected, or this filament will be guided to the nozzle of the 3D printer, and this 3D printer and this filament will be melted by using the deposits the material. And this actually, you can see the printer will have a heating element, and this heating element will melt the spool of metal, not spool of material that is coming from the coil reel, and this will be heated and the material will be deposited. So this is one of the this is how the FDM is actually working. And all the 3-axis movements, you can see X-axis movement, Y-axis movement, and Z-axis movement, all are controlled by 3-axis controller, which we generally use it in the CNC machine, 3-axis CNC machine. So 3-axis controller will control the movement in the 3D printer, and the printer will actually heat the filament coming from the spool of the coil, and which will melt and deposit precisely based on the slicing what we have created earlier, based on the STL file what we have created earlier. And these are some of the common materials, like you can see PLA, ABS, PCL, and PEKK. So PLA is the polylactic acid, and ABS is a very common material we know already. It's acrylonitrile butadiene styrene, and PCL is polycapro lactone, which is again a very similar material to the polylactic acid, and PEKK is polyether ketone ketone. So this is you have two ketone chains, so they have this name. So if you see in this, uh, the lactic the 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 material which have the lactic acid or the chain in their chemical formulation, that is actually biodegradable. So polylactic acid and PCl, polycaprolactone, are biodegradable, and biocompatibility is very high for polycaprolactone, but it is slightly limited for the polylactic acid. So you have this information. This we have sufficient information of which material is suitable for in terms of biodegradability and biocompatibility. And if you see that PCl is actually one of the common materials which is used since it has both biodegradability and biocompatibility. Apart from this, we have ABS, which is not biodegradable and biocompatible, so it is not much suited for the biomedical application. But still, it is used in some external applications which are not where the implants are not fitted in the human body. And apart from that, you can also see the typical uses. Primarily, this PCl it is used in the medical scaffolds. So this is one of the common material which is used in the biomedical application. And this PLA is also used, but primarily for the production of prototypes. And PEKK is also used for implant production. But primarily, PCl is one of the most suitable because for the case of implants, biodegradability and biocompatibility is very important. So that is the reason why PCl has gained more attention in the biomedical applications. And coming to the how this actually a composite material. So you know this the biocompatible polymer matrix that is made up of PLA, PCl, or PEKK combined with bioactive reinforcement. So again, as you know, in the case of composites, you will have a matrix, you will have a reinforcement. The matrix is basically gives you the basic structure. It gives you the outer structure so that you can include any suitable reinforcement. That's what we do generally in the metal matrix composite, where the metal will form the matrix and the composites will be made up of some reinforcement. Like the reinforcement may be graphene, graphite, or some oxide, silicon carbide, some sort of ceramic material. So similarly, here also there is a matrix and there is a reinforcement. The matrix is basically made up of the polylactic acid or PCl or PEKK, and the reinforcement is basically made up of some materials. Say it can be in the case of some ceramic materials where you need to increase the strength, where you need to increase the stiffness. So in such cases, ceramic materials can be used as a reinforcement. So this composite material, again, we can develop these materials based on the requirements, based on the implants and scaffolds, based on the mechanical strength required for the particular application. Because a biomedical implant that is used for a dental application will have a different mechanical strength requirement, whereas implant that is used to replace a bone will have a different different mechanical strength. So all this can be tailored by using this, by varying the combination of this matrix and reinforcement. Then controlled biodegradation is possible. That's what this is one of the most developing fields now. Because earlier, as I told you, when you keep a metal inside the human body, the metal remains the same. So once you want to remove the metal, again you need to perform a surgery. You have to remove the metal. Whereas in the case of the present day biomedical materials, the material actually biodegrades itself. So it actually degrades inside the human body. It does not require another surgery for the removal of the implants. And improved bioactivity for better tissue bonding. This is also one more requirement. So as I already told you, this tissues has to grow on this implant, bones has to grow on this implant, so that your musculoskeletal system is not affected. So that is also possible in the case of the biocompatible polymer matrices. So these are the typical applications of FDM printed biocompatible materials like bone scaffolds, which are used for the which are used to as a replacement for the damaged bones, and load bearing implants. Load bearing implants in the sense typically the joints where there may be a knee replacement surgery, so there may be an implant used there. So such type of load bearing implants people use. Um, um, uh, the FDM based biocomposite material. Then tissue engineering, again, when nowadays we have this sort of typically when there is a hernia treatment, there the implant or there'll be a small mesh type of arrangement will be given. A small mesh will be given uh, to have the hernia surgery. So the tissue can grow around the mesh. The mesh will be, it is not a complete solid material. So this tissue will grow around the mesh, and at the end of the day, or eventually, this will become the part of the human body. And drug delivery services, as I told, devices. So to specifically to give drugs into the human body, the cytosine-based biodegradable materials are used, and they are also produced by additive manufacturing. And biomedical relevance, you can again use materials like polymers and bioactive ceramics and nanoparticles to improve the mechanical strength. Materials like this hydroxypeptide, this is one of the very common material that is used for increasing the bioactivity. So this is typically for bone integration. So this is basically a magnesium based material. So this material actually integrates with the bone uh, in such a way that you don't find the difference between the implant and the actual and the or the nature based bone and the implants. And also this gives a good adhesion to the tissues that is growing across around the implants. And again, this you can control the degradation. So which means that there is a specific time or there is a rate of degradation for this material. So once the biodegradability starts, this tissues will grow outside around the biocompatible material, and the scaffolding structure will be degraded completely. So the entire structure will be again made up of your bone or the tissues. So that is one of the major biological advantage we have with respect to the biomedical materials. And FDM based biomedical materials, again, it is very much patient specific, and it gives you a very, very good biodegradability. And when you see the historical milestones starting from this FDM biomedical composite, so typically this FDM was used for biomedical applications maybe approximately in the year 2010. So before that, people were using all the your metallic implants. The traditionally you use machined metallic implants were used. Then FDM technology were adopted into this for the production of biomedical composites. Then around some 10 years back, we have this bioactive composites. It's a combination of PCl and hydroxyapatite, which actually gives you better bone integration, which actually gives the tissue formation on the biocomposite is very much higher in the case of hydroxyapatite. Then later, people started to include the fiber reinforcements like carbon. So carbon is basically a neutral material, so it has biological implants. And bioglass, people have developed a glass material which is similar to glass material, glass fiber, can be implanted into the human body. Acts as a reinforcement. So when you have a matrix like polylactic acid or PCl, and when you have this carbon and bio glass as the reinforcement, this actually increases the strength of the material, and primarily these are used for the joint applications. Then recently we have the hybrid FDM, which actually uses the electrospinning technology. Electrospinning technology is used to produce the fibers. So the filament what it was produced by, the filament what you have for the FDM will be made up of a material. This filament itself can be produced by electrospinning process. So electrospinning process where you can add a different material. Like I can go for customization. where I can add a PLA or I can go for a reinforcement, a different reinforcement like a bioglass reinforcement. So I can vary the combination. It is like a typical metal matrix composite. We vary the combination. So similarly, the electrospinning can be used to mix the material first. And after mixing, the material will be spun out. This spinned material will be in the form of fibers, and this will be used for the uh, FDM process, fused deposition model. And nowadays, this 3D printers are even readily available in the uh, laboratories also, most of the laboratories which are coming up nowadays. So this is how the evolution of the FDM in biomedical composites has taken. So this of late is a very recent developments. So you see that in the last 10 years only we had these developments. And so this is what I wanted to explain. So you can see there is a PLA pellet. So generally this will be in the form of pellets. So PLA pellet is polylactic acid. Then you can add the reinforcement as per your requirement. And this can be stirred or this can be made into a composite material. And this is then extruded. This is a so this material is actually extruded. It can be a twin screw extruder, where generally electrospin materials are also extruded like this. So there is an extruded, and you can produce the filament here. You can see the, the from the raw material, we produce the raw material for the 3D printer. So this is the basic raw material where people can vary the combination so that they can achieve the required strength, what they intend to achieve. Then these materials are actually developed into a fibers. Filaments. So these filaments are then actually converted, are then fed into the 3D printer, where you have the localized melting, and you already have the CAD modeling done, the STL file generated. When these files are generated, these files are fed into the 3D printer, the filament is actually melted and printed in such a way that you get the structure like this. So this is typically a scaffold. This is what I told you, a scaffold. So scaffold is a support structure for the bone. Uh, you can see different the scaffolds actually layer by layer deposition of material so that it acts as a support structure. And here you can see the uh, porosity that is given to the scaffolds, which will make the cells or the tissues to grow inside this porous gaps, this pores. And this scaffolds, if it is made up of a polylactic acid, this is biodegradable, and over a period of time, this scaffolds will degrade itself inside the human body, and further these cells will be developed. And so that this scaffold, wherever you are using the scaffold, initially it will be a implant. Over a period of time, the natural material will replace this implant, and you see that there may be some cell growth will be there. And as I told you earlier, this development of this FDM based composites, biocomposites, cannot be done alone by the engineer. You need to take the help of your physicians also. So they will be carrying out the cell studies. So whether this scaffolds, whether this material is actually compatible with the human body, human tissues, whether it will proliferate, whether the growth of the tissues and the bones, whether it is possible. So all these studies will be, the characterization will be done from there, from the physician side. So this is one of the studies which is reported in the paper. So this is one of uh, example of the usage of FDM in the biocomposite application. And further, you can see how this bioactive PLA scaffolds are made. You can see first thing they do is the 3D printing. So you can see, you can have a design of your requirement. So this design is very much customized. It can be customized and it can be made patient specific. And this design, once we make the scaffold, this is primarily for the bone implants. So this scaffolding is primarily for the bone implants, and this can have different structures. The lattice structure what is given is here is one example. This can have different lattice structures. So each and every lattice structure will have a different material strength. So this will give you the different structures that is uh, required for the patient. And once you do this, then people go for the uh, printing. So while printing, uh, you can see the components will look like this. So this actually is made up of four components. You can see this made up of four materials. Like this is first one is basic polylactic acid. Then you have PLA plus MMT. This is the second one. That is Montmorillon clay, which is again another. It is used as a reinforcement. Then you have the PLA, MMT, and SRBG. That is the strontium-based doped bioactive glass. So again, this is another biodegradable and sorry biocompatible material. And further, you add the nano hydro oxyapatite. So this is what this nano hydro oxyapatite is used for. Primarily, it enhances the tissue growth or the bone growth around the scaffold. So this is done, and also there can be some coating also given on this surface. So this is how the surface will look like. So you can see a layer of coating of the biocompatible materials also can be given, and this scaffold will be placed inside the human body, and it will be placed like this wherever required. Say for this is the case of using the scaffolds for orthopedic applications. So similarly, you can also develop uh, biomedical implants for dental applications and so on. So you can see there is a biodegradability. This is what I told you. This you have the scaffold that is produced, and over a period of time, you can see the scaffold getting degraded inside the human body. And how the biodegradability test will be done? This will be done by using a simulated body fluid experiments. You will come across uh, uh, our body will have a fluid, and the same simulated environment is there is, is simulated by using a body fluid, and this scaffolds, whatever is produced, whatever the implants that are produced, will be placed inside the simulated body fluid. So they will do the biodegradability. Say for one day, what is the degradation? For 1 month, what is the degradation? For maybe for 6 months, what is the degradation? So they will be studying the degradability, and accordingly they will be suggesting the material that can be used for producing the biocomposite. Then it should be biocompatible. As I told you earlier, in the case of stainless steel, this chromium will develop cancers inside the human body, cancer cells. So accordingly, biocompatible materials only has to be um, used, primarily the polylactic acid, the PLA family. And additionally, these materials, whatever the scaffolds, whatever the materials you are producing, this has to be subjected to the mechanical strength. You need to evaluate the mechanical strength, because this is a bone implant, which is primarily used for uh, withstanding load. So you need to uh, evaluate the mechanical strength for such material, and this also will vary. Say for example, an implant that is used in hand will require a lesser strength, whereas an implant that is used in legs or the lower limb, then the strength will be the strength required will be on the higher side. So this is one understanding you should have. Then drug release. So in the case of drug carriers like the cytosine based biocomposites, so whatever the drugs you are actually feeding inside the drug carriers should be, the drug carriers should release it accordingly over the period of time. Then protein absorption. This is also very important, because only when the biocompatible material absorbs the protein, this will further develop the uh, bones and the tissues that has to be grown around the biocompatible material. So you can see there will be a scaffold that is actually customizable. The scaffold will have the shape that is required, uh, that will vary from human to human. So this is generally, these are some of the major requirements. One is biodegradability, biocompatibility, and mechanical strength. This is for your typical bone implants, and again, protein absorption for making the tissues and bones to grow around the bones. Then drug release, if you are supposed to deliver drugs by using a drug delivery system, then drug release also is a major factor to be considered. Then some other applications. So this is one of the common applications what primarily we have been doing it of late. We have been exploring, but there are many other applications where our people can explore and people can develop products. So one is the orthopedic implants. You can see the plates, screws, bone scaffolds, which are primarily used for when there is a fracture of a human bone. These plates, screws, and bone scaffolds are used, and this is the customizable is one of the major, the basic. Then the other applications are dental implants and prosthetics. So when there is a root canal treatment, a tooth may be removed and an artificial tooth may be fixed. So for that, people will use this uh, FDM based 3D printing, and also crowns. Maybe sometimes a part of the a part of the tooth will be worn out. So on the top layer, a crown will be deposited. So all this is possible with the help of for the dental implants also. Again, with the help of CAD and FDM process. And tissue engineering, again, it comes with the help of, when there is a bone replacement, when there is a fracture, the tissues has to grow across, and vascular scaffolds like cartilage. Primarily, I told in the case of it's very similar to the treatment, where uh, you just give a support to the people affected by hernia. There is a small mesh that is provided, and this acts as a support to the hernia affected person. So around the hernia, I mean around the uh, uh, sorry, around the mesh, the tissue grows. So that is one of the major advantages. Then the role of bioactive composites, that is enhancing tissue regeneration. So the additives which you are adding should enhance the tissue regeneration. So that is the additives was one of the examples was that NHA, so which is used as the additive, which actually increases the regeneration of the tissues. Then drug delivery devices like stents and capsules, which are used to deliver the drugs inside the human body to a particular location, that also can be produced by uh, FDM process. So again, the major advantage of using additive manufacturing to produce this biocompatible implants is you can create the porous structures as based on the requirement. So that is one of the major advantages you will come across in all the applications. If you see all the applications, porosity is one of the major things that is addressed by the additive manufacturing process. In other applications, after you produce the material, uh, then also you need to have uh, the surface modification also is needed. Sometimes you call it as the histo-inductive properties. This is the property that enables the surface, I mean the bone or tissue to grow on the surface of the implant. So that is one of the important property. Then antimicrobial property. So whenever you are implanting the material inside the human body, it should not be affected by the microbes inside that is present inside the human body. Microbes like bacteria or maybe some virus. When there is some viral infection or bacterial infection, the implant should not be affected by that. So there are different bioactive coatings which are provided, which modifies the surface, and that is actually a post processing sort of application. And again, mechanical testing we are supposed to do. We can do the testing um, directly for the material that we have developed, or we can do the testing for the product we have developed. So it all depends on the application. So primarily the material is developed, then the, the material is tested for tensile, compressive, and fatigue testing. So because fatigue testing is important, because when we are fixing some implants on the human joints, so there will be a continuous cyclic load acting on that particular component. So fatigue testing is also very important in terms of the biocompatible material. Then biological testing, this is actually it's a complete different specialization where you need to assess the toxicity of the materials which are used, because sometimes the material which you are used for the uh, which are used inside the implant should not create any toxic effect on the human body. Say, for example, in the case of stainless steel implants, when the chromium content in the stainless steel is beyond certain level, then the chromium will induce some toxicity inside the human body, which will develop the cancer cells. So that has to be avoided. So cytotoxicity testing has to be done. And again, as I told you earlier, the body seminal fluids. So the whatever the material we are preparing, whatever the material we are fabricating, has to be placed inside a simulated fluid, simulated body fluid, and has to be tested for the biological testing also. So this is not. So this can be done only by the doctors and physicians, which our engineers may have a limited role in this particular aspect. So whereas in terms of surface modification, in terms of mechanical testing, mechanical engineers will have a more role to play. Whereas in the case of biological testing and clinical translation, clinical testing, the doctors and the physicians will have the major role to uh, carry out the testing. So clinical translation. So again, they will be subjected. So and before clinical translation, this also will be subjected to in vivo animal testing. So that is also one of the mandatory tests that is required for any implants, for any drugs that are tested on human body. There is a specific test protocol that is available with the animal testing. Again, we need to take a lot of permission before we test on the animals. And challenges, one of the major challenges in the case of 3D printing or in any uh, uh, metallic material, when you talk about composite materials specific in particular, this anisotropy effect will be there. So anisotropy is very simple. So when you take the case of a homogeneous material, take the case of pure metal, like it can be aluminum, it can be magnesium, it can be steel. So a pure metal will have, it is homogeneous throughout its volume. So when you measure a property in X direction, you measure a property in Y direction, you measure a property in Z direction. It can be a tensile strength across X, across Y, and across Z. All will be more or less similar in the case of homogeneous material. But whereas when you come across composite materials, this composite materials is a combination of matrix and reinforcement. So which will have the anisotropy in a, it is a default virtue of the composite materials. So you measure a particular strength in x-axis and y-axis and z-axis. There will be a major variation. There will be major changes in the case of composite materials with respect to the anisotropy, because this is a non-homogeneous material. And because of this anisotropy, sometimes there may be weak interlayer bonding, which actually has to be tested by the mechanical engineers. We need to improve the mechanical reliability of the compatible implants produced. Then sterilization is also very difficult because the material is very sensitive, because this is a biocompatible material. So it may be affected by the microbes very easily. So the sterilization procedures also is actually a major challenge in the production of biocompatible materials. And nozzle clogging, this actually happens in the 3D printing, because the composite filament will have different textures. Say for example, primarily when we are mixing polylactic acid and say for example carbon or the bioglass, this will form a texture like a toothpaste, which will not have a typical uh, uh, behavior of a liquid. It will have a different behavior. Basically, uh, this this mixture will follow and will be of a non-Newtonian fluid. you know the difference between Newtonian fluid and non-Newtonian fluid. So this will have typically of the characteristics of the non-Newtonian fluid. So this nozzle clogging and the flow of the material also has to be very important when we develop different composites, when we develop different combinations of the composites. These are some of the challenges that is observed. And, and moreover that regulatory aspects also is very important, because these biocompatible materials will be planted on a human body. So it is a lot of regulatory controls are available or to be followed for to produce such components. So it is not that we get the approval very easily. It is not that it is not our regular mechanical testing where we develop materials and we test them. But to make such materials to go for the actual application, it will take a longer period of time as compared with your traditional materials which are used for non-bio applications. And ethical considerations, again, when we develop such type of materials, the patient safety, the patient consent, all these things play a major role. That's why when we produce a component, when you produce a biocompatible implant, uh, it goes through a lot of rigorous test processes that is mandated by the governments. And some of the future research and trends, people are started to use 4D printing methods also, like bringing in the shape memory aspects. So shape memory polymers are also used as biocompatible materials, so that the after the implantation, the material is able to withstand the shape, whatever the shape that is required for a particular human being. This shape memory materials is able to withstand the particular shape. And multi-material FDM. So again, nowadays we come across multifunctional materials like materials which is having a negative Poisson ratio, where you know about Poisson ratio. When there is a compression, there is a lateral expansion. Whereas in the case of negative Poisson ratio, when there is a compression, there is a again there is a lateral compression. So such type of materials are there, functionally graded biomaterials. These biomaterials are applications like tissue transitions and to enhance the stiffness and priority. So such having multiple properties are also can be explored. But these are all research. Functionality, because this graphene or carbon family is basically a neutral material which does not affect the biocompatibility. And some materials with some electrical conductivity is also being explored, because this actually increases the formation of tissues, increases the tissue engineering. So this is one of the recent developments we have. And your traditional titanium implants, even the titanium implants, titanium alloy, that is the 6-4 alloy, which is actually the one of the common alloy which is used for biomedical application. Even these alloys, earlier they have been using it as a solid material, but now because of the technology of 3D printing, now the scaffolding type of materials can be provided, can be produced. You can produce structures with porosity, so that you can increase the possibility of bone and tissue growth on this material. So this is also a scope for research in the upcoming time. And this is, I'm not sure how far it is going to. I mean, basically we have not worked on this so far. Even we have, as I told you earlier, this is one of the initial stages of. We are also going through a lot of new experiences when we are working on this. So AI-driven design and integration, maybe people suggest there are some literature available so that they can develop some algorithms so that the implant geometry can be optimized, but it's a very large area to explore and to optimize the mechanical loads, to optimize the biological